Hello everyone, my name is Soham Nag. In this presentation, I would like to explain my work on SmrtComp, which is an intelligent and online CAN data compression tool. I have developed this work under the guidance of Professor Smruti Ranjan Sarangi, and our work has been accepted at the IEEE International Conference on Intelligent Transportation Systems in 2023. As illustrated in the accompanying image, modern vehicles generate a vast amount of data, posing significant storage challenges. In our research, we propose a solution to tackle this issue. So this is how our presentation will go. We will begin with a problem statement followed by motivation and related work, then provide the necessary background for our work, which will be followed by algorithms, proposed algorithms, experiments, and evaluation. Finally, we conclude and discuss the future work. Modern cars have 100 plus ECUs, and CAN is the de facto for this ECU communication, on which data is generated at a rate of 500 kbps. This data, when stored, can be used for many purposes like fault analysis, driving pattern, accident analysis, performance monitoring, and others. So here we propose a novel solution to store this CAN bus data, which is SmrtComp, and this dynamically compresses the CAN data. Having established the fact that a lot of data is being generated by modern vehicles, we first need to understand what are we gaining by storing such data. So we will first discuss the importance of long-term storage of CAN data, followed by EDR storage system requirement. Then we move on to discuss some problems associated with conventional storage solution. Finally, we will provide our solution, which is SmrtComp. In modern cars, increasing ECU complexity generates significant amount of data, which is roughly 25 GB per hour, necessitating efficient storage solutions. So efficient data logging also allows us to find the root cause analysis, courtroom evidence, insurance claim, detecting cyber attacks. So for all of these, what we need is that the data should be accumulated over a long period of time. So for example, in case of anomaly driving detection, we need to store the data for roughly about 250 hours. That is the minimum requirement. And so what helps in this is that there is EDR, which is Event Data Recorder, helps to record this CAN bus data. This slide talks about some of the use cases of ECU data in great detail, which has been explained in the previous slide. Now coming to storage system requirements, durable and robust TDR storage solution is essential for withstanding tough automotive conditions and frequent writes by numerous issues in addition to being resilient to security attacks. Flash memory and EEPROM can't be used as a storage solution for EDR as it doesn't possess the necessary requirements for an in-vehicle data storage system. Here, FRAM and automotive SD card comes handy as they possess all the necessary features. So in comparison to the massive volume of data being generated by 100 plus ECUs, the sizes in which FRAM and SD cards are available is very less. Hence, we need efficient CAN data storage solution. The question arises how to store such massive volume of data. So one solution could be to expand the storage, but this is not feasible due to high cost of FRAM or automotive SD card. So the another solution could be to periodically archive the EDR data into an external SSD or cloud. But this solution also has its own disadvantage due to reliability issue, cost, or privacy issue and other reasons. So the final solution is that we can compress the EDR data. So whenever EDR memory saturates. So compression can be of two types. One is lossless or lossy, and we could use another approach which is a hybrid technique, and it adaptively compresses the data using both lossy and lossless algorithms. We have been referring to CAN for quite a while. So what is a CAN? CAN is a de facto for ECU communication. It is a broadcast-based serial communication. CAN message frame something looks like this. So please have a look. And when multiple ECUs concurrently try to send messages on the CAN bus, an arbitration based on message IDs is done to allow only one ECU. So let us understand this by taking an example. So we have two ECU, let's say denoted by node A and node B, and these are the message IDs allocated to them. So from this, the node A is allowed to send because its first 0 bit is at index 3, uh, while the uh, first 0 bit for node B is at index 4. So node A is allowed to acquire the CAN bus and send its data. So CAN messages can be configured with a DBC file, which is a CAN database file. Moreover, CAN message can have multiple signals as received from multiple ECUs. Silver is a software to simulate virtual ECUs in form of modules. It allows us to add and configure the CAN messages via CAN database file. We have used Silver to simulate the ECU environment for our experiment. Now coming to existing work and its limitation, lossless based solution uses GD algorithm to selectively remove duplicate packets. But as this solution uses lossless algorithm, hence it has less space efficiency and also data quality is not tunable. So lossy based work uses PLA. This method gives the ability to tune data quality but does not uses the high correlation feature which is present in CAN signals. Another recent lossy based work uses JPEG compression to store video data, but it defines only two levels of compression quality, and it also doesn't utilize the correlation of vehicular data. Now we have discussed lossless compression where there is no information loss but limited storage efficiency. Similarly, for lossy compression, although it has tunable compression gate, but there is a high RMSE. So the key idea is to build an intelligent compressor using the advantage of both lossless as well as lossy compression, giving birth to hybrid compression. So the first question which arises is what is an intelligent recorder after all? So we can treat an intelligent recorder as something which adaptively compresses the data based on data recency while maintaining the QS criteria, where whose one input is the CAN bus data and output is compressed data. So this QS function in our experiment is an exponential function, uh, and we will be discussing this function in detail in the later slides. So the next question is how to store this data. So as there are 100 plus ECUs in modern vehicles, so if we try to log individual signal, it will be a difficult task. So what we do, we group multiple signals into a frame and we will log that frame into a secondary storage. So as you can see in the diagram, so this is how a frame looks like, where each row represent the data signal states and each column is the data signal. Now we will discuss our proposed algorithms. So this algorithm discuss about the macro frame creation. We add incoming CAN signals into a frameless data structure is denoted by FB, and we continue to do the same till the list saturates or reaches its maximum size. As the frame list reaches its maximum size, we do lossless compression on the frame and add it to a macro frame list data structure denoted by MFB. And now and when an MFB gets full, we lock the or reaches MFB reaches its maximum size, we lock the entire macro frame into the secondary storage and empty macro frame list to create room for the next frame. Now we discuss the log compression algorithm. Here alpha and beta are two user defined values based on which we decide whether to apply lossy or lossless compression or to discard the frame at all. We continue to log the macro frame till the log reaches its maximum capacity. If the log saturates, then for every frame in the log, we will first calculate the compression level denoted by CLI. This is obtained using the function FI or the QS function as discussed earlier. Now, if the compression level is greater than equal to alpha, we will discard that macro frame. And if the compression level is between alpha and beta, we will call the compress MF function. So this compress MF function, what it does is that it recompresses all the frames within that macro frame to a compression level of CLI. We then replace the macro frame with the new recompressed macro frame so as to create room for more macro frames in the log. So now we continue this process for all the macro frames in the log. Finally, at the end, the log has been recompressed, and we now have room for more new macro frames. This algorithm discuss about the uh, tunable lossy compression algorithm. So this expects a compressed macro frame list and the desired compression level as an input. Initially, we declare an empty list MFC dash, which will store all the answers or all the recompressed frames. And now for all frame in MFC, which is the macro frame list, we do frame reshaping followed by lossy compression of that frame to the desired compression level, that is CL, which is given as an input, and add this to our result list, which is MFC dash. And we repeat this for all the frames in the list. And finally, we return our answer as MFC dash, which contains the recompressed frames. Please refer to this slide to find the meaning or definitions of the notations which we have used while explaining our algorithm. So the first step in the construction of compressed frame is lossless compression followed by PCR dimensionality reduction algorithm. So in a canvas, the signals are highly correlated. So we apply PCA for dimensionality reduction. So the number of signals are reduced from n to n dash, which is followed by DCT lossy compression. We set a threshold for DCT, and all the fields which are having values less than that threshold are removed. Here in the diagram, X indicates the removed values which has been removed. So finally, after this, we get the compressed frame. And for every compressed frame, we maintain a bitmap. So now for every compressed frame, we want to decompress the frame and get back the original frame. And for this, we need to know which fields has been removed or modified or has been kept intact. For this, we maintain a bitmap where we maintain a bit for every field in the original signal. And this bitmap is used during frame reconstruction. Frames are typically in KBs and they saturate in no time due to massive amount of data being generated by numerous ECUs. So if writing new frame to secondary storage is expensive, so what we will do is that we will group frame into macro frame, and group of compressed macro frame forms a log, which is locked to secondary storage. So this is how a macro frame looks like. As you can see, this K1, K2, KL, this is the bitmap for every frame, and this orange part is the frame, and this collection, these are grouped together to form a macro frame. Now coming to frame reconstructions, we have a macro frame. From there we will extract the frame which we want to reconstruct. And so as discussed, we have for every compressed frame, we have a bitmap. So we will do the reverse operation of frame construction. Like at first we will do that inverse DCT using bitmap. So all these removed X values will be replaced with the actual or estimated values, which is nearly equal, and followed by inverse PCA. So after doing inverse PCA, all the correlated signals which were removed are now brought back to form the original reconstructed frame. So as you can see in the figure, so all the signals as well as their attributes are regenerated, and frame is finally reconstructed. As we are compressing older frames using lossy compression, which is a tunable algorithm, using a tunable algorithm, the quality of the data will gradually reduce over time, and also the reconstruction of the frame from the older compressed data becomes pretty much difficult. Hence, we discard older frames. But the decision to discard or on after what period of time we will discard or preserve the frame is based on two user-defined hyperparameters, alpha and beta. So this graph depicts when to discard a frame, when to apply lossless compression of a frame, and when to use lossy compression. On the x-axis, we have used macro frame index, which tells the age of a macro frame, and on the y-axis, we have used compression level. And this graph, like the value, we can get using our QS function. So high value of alpha, if we choose high value of alpha, we are allowing quality reduction in older frames. While low value of beta discards lossless frame, prioritizing data efficiency over quality. Like we are prioritizing high CG, high compression gain, and giving less priority to RMSE. Now the question is, how should we choose alpha and beta? That is, what are the factors on which they depends upon? So the selection of alpha and beta relies on user preferences for the trade-off between storage efficiency, that is the compression gain, and the data quality, which is RMSE. The question becomes, whom should we give preference to between RMSE and compression gain while choosing the values of alpha and beta? So the answer is, ideally we should give equal preference to both RMSE and compression gain. And the exact thing is done by our algorithm, which is SmrtComp. So SmrtComp excels and balances both compression gain as well as RMSE, thereby surpassing lossy algorithm by 94.33% in RMSE and achieving 3.2 times higher compression gain than lossless algorithm. So this is how our evaluation on experimental setup looks like. We have used three different data set to test SmrtComp's performance. One was used in a prior research work. The second one being the Unity card dataset, and third one is the in-house generated driving data. So we tested using an ECU simulator, which is silver, and the entire thing was run on Beaglebone blackboard. The specifications are listed as you can see, and we have used a automotive SD card as a 4 GB automotive SD card as a secondary log solution. We compared different state-of-the-art lossless algorithms in different driving scenarios. So from the graph, it is evident that deflate has the highest compression gain with the shortest compression time. Hence, we choose deflate as the lossless compression in our SmrtComp algorithm. Similarly, we compared various lossless algorithms, and from the graph, as you can see that DCT gives a good compression gain as well as low RMSE. So we choose DCT as our lossy algorithm. Also, as can be seen from the heat map, that CAN data signals have high correlation, uh, and hence we use PCA for dimensionality reduction for a better space gain. Okay. Coming to the results, state-of-the-art lossless algorithm can store about 128 frames, while SmrtComp can store more than 400 macro frames, followed by lossy algorithm, which can store 800 macro frames but at a cost of high RMSE. Considering the log size of 4 GB, SmrtComp saturates the log in 10 days, while the lossless algorithm saturates it in 3 days. Also, SmrtComp completes recompression within 4 minutes, considering inter-arrival time of 34 minutes for 32 MB CAN macro frames. So, in order to evaluate the efficiency and performance of SmrtComp, we calculated the compression gain and RMSE of SmrtComp lossless and lossy, and all of them were compared. So from the graph, we can see that for lossless compression algorithm, it has the lowest RMSE but has the worst compression gain. For lossy algorithm, it has the highest compression gain but worst RMSE. And as discussed in previous slides, there has to be we have to maintain a balance between compression gain and RMSE. From the graph, it is evident that SmrtComps wins in all the cases, as it strikes a balance between CG and uh, RMSE. So to check the accuracy of SmrtComp, we reconstructed the vehicle speed, acceleration pedal, and steering angle data from the lossy compressed data. So in the graph, in all the three graphs, the blue line is the original signal and the orange one is the reconstructed signal. So the close overlapping between the two lines in all the three graphs assures the SmrtComp's accuracy. For our experiments, we have used an exponential QS function, but to demonstrate the flexibility of SmrtComp, we have shown that we could have also used a linear function as well. So this graph depicts the distribution of CG, RMSE, and memory used of compressed macro frames for different functions as a choice of QoS. Also, it can be seen that the dashed lines, that is the curve fits in figure B, clearly shows the error curve is in accordance with the compression gain in figure A. In order to evaluate the efficacy of SmrtComp, we plotted a graph which depicts the time taken to saturate a 4 GB secondary log at each compression level. That we have evaluated SmrtComp's efficiency, it is important to ascertain that the important features or anomalies of the original data are preserved in the lossy compressed data. So in order to do so, we ran anomaly detection algorithms in both compressed as well as uncompressed data and compared the anomalies in the two results to check SmrtComp's accuracy. In order to find out the misclassification in uncompressed as well as compressed data, we first ran state-of-the-art driving anomaly detection ML algorithms on the uncompressed data to find out which algorithm suits the best for our data set. We have used grid search CV for hyperparameter tuning, and after numerous iterations, we finally found out that isolation forest or iForest is the best for our case. We then ran anomaly detection algorithm, which is isolation forest on the uncompressed data. After this, we gathered the compressed data across each level and then decompressed it. After this, we ran isolation forest algorithm on the decompressed data, and finally we compared the anomalies in the uncompressed data and the compressed data to find out the misclassification percentages in both of them, and finally compared them to find out the efficiency of SmrtComp in retaining the important features or anomalies in case of uh, compressed data. Few of the key observations: misclassification rates became unacceptably high beyond the compression level of 10, hence we restrict to 10 level of lossy compression. As the misclassification rate across each level was within the acceptable range, hence SmrtComp was able to retain essential features despite lossy compression. Hence SmrtComp effectively preserves critical anomaly information while reducing the data size. This graph depicts the rate of misclassification at each level of lossy compression. The average misclassification rate is around 23%, which is well within the acceptable threshold of 25%. To the best of our knowledge, this is the first hybrid and tunable compression system in this domain, which can store and compress scanned data at line speed that is of 500 kbps. Moreover, SmrtComp beats the state-of-the-art lossy algorithm by 94.33% in terms of RMSE and achieves 3.2 times higher compression gain as compared to the state-of-the-art lossless algorithm. We aim to extend our approach to encompass drone signals as a future work. Also, in our experiments, we have used automotive SD cards as a secondary storage solutions. We intend to work with FRAM systems also and develop a suitable middleware for the same in our future work.